Bismillah ar-Rahman ar-Rahim. This is Control Systems course, and I would like to deal with Laplace and inverse Laplace in this lecture. This lecture will comprise of 120 minutes of recording, which will be equivalent of 3 lectures. So 40 minutes for first lecture, next 40 minutes for next lecture, and ultimately the third one, 40 minutes will be the third lecture. And in control systems course, the foremost important thing is to make a mathematical model for electrical, electromechanical or mechanical system, rotational systems, and then finding out its solution output in time domain. So we need to model, when we need to model mechanical system or electrical system, it has some differential equation. It will be in the form of derivatives or integrals, and ultimately the equations that will describe the system will have maybe multiple integrals and multiple derivatives in the system. And we know that finding out solutions in time domain for these integral differential equations will be a difficult task. There is a need of translation of these integral differential equations into a simple linear algebraic equations. Finding out solutions for linear algebraic equations is much easier than solving it in time domain. Ultimately, converting these frequency domain equations, which is linear algebraic equation, and back converting it to time domain using tabular forms or complex integration, both are possible, and we'll have solution in time domain. So first of all, we'll try to assume that the system is already being modeled and we have a differential equation present with us. Now from onwards, finding out solution of this differential equation in time domain or converting it into frequency domain and solving it after the solution, transforming it back into the time domain is the question which will be dealt in next 3 lectures. This is the introduction of Laplace and inverse Laplace. Using Laplace, we translate integral differential equations into simple linear algebraic equations. Solution of linear algebraic equation is simpler than solving it in time domain and then finding out inverse Laplace transform to have a solution in a time domain. So that's easier method, and most of the control system course we used to do it in the same manner. We may have solution in time domain, which is known as steady state, which is known as state space modeling. So we'll try to touch that state space modeling at the end of the course, maybe at 27, 28, and 29 lectures. Lecture number 28, 29, or 30. For the time being, rest of the course of control system is always around finding out solutions in frequency domain, solving them in frequency domain, and then back converting them into a time domain. So this is the method that will be followed throughout the course, except for a few lectures at the end. So let's try to learn about Laplace and inverse Laplace transforms once for more, because you already have studied it in the previous course of signal systems, and it might be appearing somewhere else like circuit analysis 2, and some of that is already being dealt in electronics 2. So we'll carry on from from Laplace and inverse Laplace for the revision purpose. As this will be a revision, so we'll just following it and just doing it at a fast pace so that all of the Laplace and inverse Laplace transforms can be covered in the 3 lectures. Modeling in frequency domain. We'll talk about review of Laplace transforms. We'll talk about learn how to find a mathematical model called a transfer function for a linear time invariant electrical, mechanical and electromechanical systems. It's always assumed in this course that the system under discussion is linear system, and it is also a time invariant system. For nonlinear systems, we have to linearize them first, and then we have to apply the Laplace or inverse Laplace transforms. Because Laplace transforms is a linear function, it will only be applied on linear systems, and similarly the time variant systems will not be dealt in this course. Rather, you may have not seen any nonlinear system or any time variant system throughout the engineering course. So Laplace transforms will be a linear function that will be applied on a linear system, and that linear system is also considered as a time invariant system. And one more thing that we'll try to assume here, that all systems will be dealt here in the course of controls are causal systems. The causal systems will have the effect of the system coming after the cause. So let's say the cause happened at t is equivalent to 0. At time t is equivalent to 0, some cause has happened. The response is only be coming after the cause has happened. So the effect is afterwards, and the cause is first. So if anything or any change happened at time t is equivalent to 0, then the response is coming after t is equivalent to 0. That will be a simpler or understandable definition of a causal system. There are other complex definitions for causal systems, but let's try to understand it from common sense. That if cause happened and afterwards the effect is coming, then it's a causal system. And mind it that in engineering we don't have any non-causal systems that we are dealing, especially for the course of electronics. All systems will be studied as causal systems, or all systems dealt in the course of electronics or the course of circuit analysis or the course of controls. All systems are causal systems. All systems are linear systems, and all systems also are time invariant systems. We don't deal with time variant systems or non-linear systems or non-causal systems. So if we have some system which is a non-linear system, that has to be linearized first, and then we'll take any transformation through Laplace transforms or inverse Laplace transforms. We'll try to linearize some non-linear systems as well to have a taste of a non-linear system, but mostly the course is covered with linear systems only, or time invariant systems only. And most of the times, as we are electrical engineering or close to electrical engineering, so most of the times we'll be modeling electrical systems rather than mechanical or electromechanical systems. The same way that we are talking about electrical, electromechanical or mechanical systems, rotational systems are also existing, but we also assume that these rotational systems are time invariant systems and linear also. Because we may have many many details for for a system such as a mass attached with spring, like aging is the effect, which can be dealt under the time domain analysis or frequency domain analysis, but aging of that mass attached with a spring is not studied here. Similarly, other variables such as temperature, pressure, humidity, these are the things which makes the system more complex and more nonlinear. So we'll try to have systems, simple systems, which are easy to deal with, and they will create an understanding of the course rather than dealing with the nonlinear systems or modeling the nonlinear systems. So we'll have something like a linear system, time invariant system, and we'll try to learn the course curriculum on top of these linear time invariant systems. Otherwise, we'll be stuck in dealing with nonlinear systems or dealing with the complex systems. So that's why we try to keep things simpler for mathematical modeling, and after having a system in integral differential equations, we'll try to solve them using Laplace or inverse Laplace transforms. That's enough for this slide. Let's move on. This is introduction to modeling. We look for mathematical representation where the inputs and the outputs of the system are distinct and separate parts. Like below in the figure, we have a system in the middle. We have inputs in terms of R of t and outputs in terms of C of t. If we have a system that has some input and that has some output, let's say the system itself is not present. If the system itself is not present, we can consider that the system is a black box. So we only have inputs and we only have outputs, and the system is a black box. There's a question that can we describe a system using inputs and outputs? Yes, definitely. We can describe the system by looking at its inputs and outputs. So if we have an output C of t and inputs as R of t, let's take them into a frequency domain. That will be C of omega as an output and R of omega as an input. So if we divide C of t, or we'll take the ratio of C of t to the R of t, then it will become a transfer function. And this transfer function is exactly describing the system and describing the internals of the system. So first we'll have to think about this system that may have representation in terms of differential or integral equations, or having multiple orders of integration and multiple orders of higher orders of differential equations. So we have to keep them in terms of frequency domain, and then we'll have to take a ratio in terms of output to the input, and that output to the input is defining the system. So we look for the mathematical representation where the inputs and outputs and the system are distinct and separate. Also, we would like to represent conveniently the interconnections of several subsystems. For example, we'd like to represent cascade interconnections where mathematical function called a transfer function is inside each block. So we may have another system which has three subsystems. Let's say output C of t is the total output coming out of these three subsystems, and input R of t is present at the input. So if we translate this system into time domain, then this subsystem 1 will be convoluted with the subsystem 2, and subsystem 2 will be convoluted with the subsystem 3. So in this way, all of these subsystems are convoluted to each other, while in frequency domain they are multiplied with each other. So this multiplication in frequency domain is known as cascading. We know that multiplication in time domain will change into convolution into frequency domain, and vice versa is also true. So if we have subsystem, three subsystems feeding the input of the first subsystem is R of t, while the output of first subsystem is going and treating as input of the other subsystem, and similarly the output of the second subsystem is going and treating as input of the third subsystem. So the total output divided by input is the total system, and we have a cascade representation of the system. Mind it that this cascade representation of system is not only the possible solution, but we may describe this subsystem 1, 2 and 3 in a parallel form as well. And this can happen when we divide when we apply partial fractions in frequency domain, and the product will change into summations, and the summation will be representing in terms of parallel connections, and the output will be addition of all these subsystems. And there's a third representation which is known as polynomial divided by a polynomial representation, when we have polynomial at the top and polynomial at the bottom. So we can also represent the system without making subsystems. We can take as a whole system and we can model it also. There is a possible solution for these polynomial divided by polynomial type of situations. So that will be a third representation, but mostly we treat the systems as cascade systems, which are represented here in this form. One more thing about these systems is that when you want to describe the system in time domain, subsystem 1 subsystem on the left will be convoluted with the rest of the subsystems, and this convolution is a difficult process in time domain, so we want to convert it into Laplace domain so that we have simple multiplicative systems. That's another representation, or that's another easier way of solving these subsystems, that we break down complete or a complex subsystem into small parts, and then taking these parts into frequency domain, just multiply with each other, and we'll have a final form, and then we can take Laplace inverse Laplace transforms to have a solution in, or the output in time domain. So the output, finding out the output in time domain is the purpose. So if the input is changed, the system output will have changed. But first of all, let's take delta t as an input to any type of system, and we'll try to find out output of the system. If you convert delta t in frequency domain, that will become 1 for frequency domain. So output will be whatever output is coming as treated as transfer functions, because the output or C of omega divided by 1 will be the system representation. So the output itself is the system representation. That's the meaning of having delta t input. If we have delta t input at the system, it means that we are trying to find out what is the characteristics of the system, how the system is behaving. This is what we are trying to find out by giving it delta t as an input. Similarly, we have other possible sets of input, and the most common sets of inputs are something like delta t, u of t. We know that what is u of t? U of t is a unit step function that starts from time t is equivalent to 0, and it is present till t tends to infinity. So delta t and u of t are two most common inputs. Other common inputs are something like ramp or unit ramp, or similarly another possible input is exponentials, e raised to the power minus alpha t, something like this. And other possible input is sinusoidals. So these are the common inputs. If we try to remember these common inputs, or if we try to analyze these common inputs, we can create any type of input or any type of a signal by using exponentials, or by using sinusoidals, or by using delta t's, or by using u of t, or the combinations of all these inputs. We can create any type of mathematical function, any type of a signal, or any type of system. We can represent all type of systems and signals with the help of only 3 or 4 mathematical functions: delta t, u of t, exponentials, and sinusoidals. One more thing that we would like to add here is that for Laplace transforms, we may think that Laplace transform may exist for any type of mathematical function, which is not true. But we deal with only those mathematical functions whose Laplace transforms exist. Giving a general description of Laplace transform doesn't exist for all type of mathematical functions. It exists for few type of mathematical functions. For rest of the functions, we may have to find out convergent solutions for those specific signals or specific systems whose growth rates are more than exponentials. And we don't have to study all the functions whose growth rate is more than exponentials. And normally all the polynomials, all the unit step functions or the sinusoidals, they have growth rate lesser than the exponential. So we can find out almost all type of functions, and we can have Laplace transform of almost all types of mathematical functions. So that's it for this slide. A Laplace transform review. So as this is a review, I will talk about this review at a faster pace. A system representation by differential equation is difficult to model as a block diagram. On the other hand, a system represented by a Laplace transformed differential equation is easier to model as a block diagram, and that I already said it. The definition of having Laplace transform is defined as Laplace transform of f of t is equal to f of s, where s is sigma plus j omega, and sigma is a real part of that complex number and omega is a frequency. And that is equivalent to integration from 0 to infinity f of t e raised to power minus st dt. In this way you can see that the time is being integrated out, and whatever is left is with s. So the function f will become f of s, and s is sigma plus j omega. So the time domain is going to be converted into s domain, where s is sigma plus j omega. Most of the times we put sigma is equivalent to 0, and we only study for j omega. That's the definition of a Laplace transform. If we put sigma is equivalent to 0, that will become Fourier transform. And Laplace transform is only a generalized version of Fourier transforms. Where e raised to the power s of t is a generic function, and we want to take projections of f of t on various sets of e raised to power minus s of t. These e raised to power minus s of t are orthogonal functions, and we can hence represent f of t in terms of f of s, and e raised to power s of t is a set of orthogonal functions whose magnitude is equivalent to 1. So we may define a new coordinate systems based on e raised to the power minus s of t, whose projections f of t is going to be projected on those functions, on those orthogonal functions or orthonormal functions, and we want to study it in some other domain, and that domain is known as Laplace transforms. So here we have a definition of a Laplace transform. Likewise, we have Laplace transforms, we have inverse Laplace transforms to convert a frequency domain function into a time domain function. So we have, let's say, f of s as a frequency domain function, minded that f of s, this f is capital, while f of t, this f is small. So it's a convention that time domain signal is being represented with a small f, while frequency domain signal is represented by capital letters. So f of s with the Laplace inverse is equivalent to 1 over 2 pi j integration sigma minus j omega to sigma plus j omega f of s e raised to the power st ds. So in this way, d of s is being integrated out, and the function is left with f of t, u of t. U of t is only showing that system is causal, and we stated it earlier that all systems that we are going to deal with are only causal systems. So here we have a Laplace transform review, and we are talking about Laplace transform tables. So few of the common Laplace transforms are presented here. Like item number 1 is delta t. This is the most common type of input, as I said earlier. U of t is another input. Similarly, gut, it's a ramp function. I talked about it, that these three are common inputs. And similarly, t raised to the power 2, 3, 4, 5, t raised to the power n u of t is another common function. Similarly, exponentials and sinusoidals are other common inputs. So if we have a delta t as is in terms of f of t, we can translate it in terms of f of s, and that will become 1. Similarly, u of t, 1 in f of s means that we are trying to test the system for all type of frequencies. The magnitude is 1 for all frequency omega is equivalent to 0, 1, 2, 3, and going on and on till infinity. While delta t is only present at t is equivalent to 0, where f of s is present everywhere in frequency domain without having any attenuation in the amplitude of frequency domain signal. Similarly, u of t, which is a step function, has got Laplace transform as 1 over s, and we can prove all these functions by applying f of t e raised to the power minus s of t, and then integrating it from 0 to infinity time d of t, and then we'll be having a function f of s which only exists at 1. We may test it, and we may verify this table, and we'll try to verify few of the entries of this table by taking out integration process, and then we'll remember this table, always try to remember this table, and we'll try to apply this table rather than always integrating out f of s, f of t. Few other functions like e raised to the power minus alpha t times u of t is known as rotation in time domain, and that will be changed into a translation in frequency domain. Remember that u of t has a transfer function of has the Laplace transform as 1 over s, while e raised to the power alpha t is just a multiplier to u of t. Then this u of t will be translated a little bit. How much is translation? That is known as e raised to the power minus alpha t. The rotation is going to change out into translation, and this translation will be appearing at s plus a. So the rotation, which is a times, that is being translated in frequency domain. This minus sign is just stating out the clockwise or anti-clockwise rotation. So let's just keep things in our mind that whenever it's e raised to power minus alpha t, the translation is in positive side. It is 1 over s plus a. Similarly, sine of omega t, u of t is omega divided by square plus omega square, while cos of omega t, ut is s over s square plus omega square. So in all of the functions, you may notice that u of t is always present, which is only stating out that the system is causal. So whenever system is causal, we may take Laplace transform of it or inverse Laplace transform of it. Otherwise, we'll just refuse to take Laplace or inverse Laplace transforms. So this u of t is just representing that the function exists only after t is equivalent to 0, and it remains forever after t is equivalent to 0. While the actual representation is on the left hand side, that is sine omega t or cos omega t or e raised to power alpha t or t raised to power n or t or anything else. The function is on the left side, while u of t is only limiting it out for the positive values of t. So here we have a Laplace transform and inverse Laplace transform table. So whenever we have to translate delta t, we don't have to integrate it out. We just conserve this table, and we'll write down the values of f of s. Similarly, if we have f of s, we can back translate into inverse Laplace transform, and we will be in the time domain function, and we can just write it down from the table. So the functions are generally like this. So we'll be applying the table entries rather than performing complex integration, although we'll try to learn it as well, but will not apply for all the cases. We'll just consider that it is present, and we'll just it's present with us, and we'll just apply the outputs of the table and find out whatever is the f of from f of t f of s, or from f of s we can find out f of t using this table. There are other tables for other least common functions, but generally, as I said earlier, that most of the times we have input something like delta t, u of t, tut, and e raised to power rotation, e raised to power alpha t, and sinusoidals. And all rest of the functions that can be created with the help of these functions. So we don't need to study anything else or some specific function that will be studied for some specific topic. So that's it from this table. So let's find out some Laplace transforms using integration method and then comparing it with the table. So let's say f of t is the function e raised to power t, and we want to find out Laplace transform of e raised to power t. So first we'll take e raised to power t multiplied with e raised to power minus s of t and integrate it from 0 to infinity as shown here in the equation. So e raised to power t has the same base as e raised to power minus s of t, so we may combine them together in the next step. So integration from 0 to infinity, e raised to power 1 minus s times t dt is the function that is being integrated out. We know that integration of e raised to power t is same as e raised to power t, it doesn't change. The only thing is whatever is the constant attached with t will come down as 1 over s, 1 over 1 minus s. So it is 1 over 1 minus s, e raised to power 1 minus of s times t, and limits will be applied from 0 to infinity. So if we apply 0 here for the values of t, it will be e raised to power 0, and the function is 1. E raised to power 0 is 1. While if we apply infinity on the other side, this will become e raised to power 1 minus s times infinity, which will be 0. We may think that we can say that e raised to power 1 minus s times t tends to 0 as t tends to infinity, which is true for real values of s which is greater than 1. For all greater than 1, we may take it as e raised to power 1 minus st going to 0 because the function that we are going to be integrated out is e raised to power minus st, and we know that the function is going downwards. E raised to power minus s, by the nature of e raised to power minus s of t, it is going downwards, and when it is going downwards it will approach towards 0 after some time. So we have 1 minus we have the total solution as 1 over s minus 1. We may think about another terms. What is the magnitude of e raised to power 1 minus st? We may notice it's rotation just, and it is e raised to power minus j real part of s of t, and it goes to 1. Magnitude of e raised to power minus j s real part of s times t is equivalent to 1. So the magnitude of any complex number e raised to power j, omega, or t, that's 1 always. The integration defining f makes sense for all s belongs to capital C, with the region of convergence or real part of s going to be greater than 1. So the region of convergence of s of f is only for the real part of s greater than 1, but resulting the formula doesn't make it makes a sense, so we'll just ignore rest of things, and Laplace of e raised to power t is 1 over s minus 1. We may think in terms of the table that e raised to the power t is just not e raised to power t, because it's e raised to power t u of t. That's why we are going to take integration from 0 to infinity. Otherwise we'll be taking out integration from minus infinity to infinity. So as this function only exists for t greater than 0, then this is the other reason of taking limits of integration going from 0 to infinity rather than from minus infinity to plus infinity. Another example of unit step function is presented here. Let's say the constants or unit step function is f of t is equivalent to 1. 1 means that it only exists for t greater than or equivalent to 0, and its magnitude is 1. This is being integrated out. 1 is being integrated out easily when it is multiplied by e raised to power minus s of t. So it is integration going from 0 to infinity. And where is u of t gone? U of t gone and absorbed in the sign of integration, where we are taking integration from 0 to infinity rather than from minus infinity to infinity. And the values of function f of t, which is 1, is being multiplied out with e raised to power minus s of t, taking integration in terms of derivatives or in terms of time. So it is d of t. So the total function that is being integrated out is e raised to the power minus s of t, because 1 multiplied by e raised to power minus s of t is always e raised to power minus s of t dt. And we again know that integration of e raised to power minus st is e raised to power minus st divided by minus s. So this minus s divided by minus s can come out of this function, and it will be minus 1 over s times e raised to power minus st, and the limit is going from 0 to infinity. Mind it that this limit will be substituted in place of t, and the method is that we first of all will apply the higher limit, upper limit, minus lower limit. So when we apply the upper limit, it is e raised to power minus s of t. When t tends to infinity will become 0. So it is 0 minus when 0 is applied, it is minus 1, and that minus 1 will be remaining, and that will become 1 over s, and the negative sign is being absorbed with that negative sign, which is coming out of the function e raised to power minus s of t after being plugged in the limits. Provided we can say that e raised to power minus s of t goes to 0 as t tends to infinity. We know that when t tends to infinity, it is e raised to power minus something, which is true for real parts of s is greater than 0. From here we can define region of convergence for Laplace transforms, but we don't have to define it for time and again here and in the next slide. So let's say that region of convergence exists for real part greater than 0, or it exists at least somewhere, and the f of t has got, if f of t has got value equivalent to 1, which is unit step response, and its Laplace transform will become 1 over s. While we can confirm this statement, f of t is equivalent to 1 if u of t, and we can confirm it with the table which is presented in slide number 6. That the table also states that if f of t is equivalent to 1, its f of s, which is Laplace transform, will become 1 over s. So if it is 1 over s, it is decaying down. It will be decaying down with increase in f, with increase in s, while f of t time domain function is 1, which is constant forever starting from time t is equivalent to 0, and doesn't decays down and doesn't grows up. It always stays like 1 forever. Its frequency response is 1 over s, which is decaying with the increase in frequency. So far so good for the lecture number 1. You might have studied Laplace transforms previously as well, so I'm not going into much of the details. We just try to apply integration and just try to confirm it with the table. So the lecture number 1 only comprises of finding out Laplace transforms, what is the total scenario of having system model in terms of differential equations, and how we can apply Laplace transform to solve these differential equations, how we can take Laplace transform, still inverse Laplace transform yet to be explored, which will be explored in the last lecture.